Alright, welcome to the AI Research Roundup, everyone. I'm Alex, and today we're diving into a fascinating paper published on May 12th, 2025, titled Continuous Thought Machines. This work really challenges the way many current AI models operate by bringing back the crucial element of neural timing, something often simplified in deep learning. The researchers introduced the Continuous Thought Machine, or CTM. It has two key ideas. First, neuron-level temporal processing, where each artificial neuron considers the history of signals it gets. And second, it uses neural synchronization, which is the coordinated firing of neurons, as a latent representation. A latent representation is essentially a compact internal code the AI learns to capture important features. So it's really about how these artificial neurons process signals over time and how their synchronized firing patterns become a meaningful internal code. And it's great to see they've also released the code for this work. So in the GitHub repository, you'll find all the necessary code to reproduce their findings, organized into folders for tasks, models, and data, which is super helpful for the community. Okay, so this first figure really gives us a great visual overview of the continuous thought machine architecture we were just talking about. It shows how the system processes information through several key stages. First, there's the synapse model, labeled as 1. This part takes the previous post-activations, which are the neuron outputs from the last step, and also attention outputs, and it computes what are called pre-activations. These pre-activations are essentially the input signals for each neuron. Then, as shown in 2 and 3, each individual neuron uses its own private neuron-level model to process a history of these pre-activations. This allows each neuron to learn unique temporal patterns. The output of this stage, at 4, are the new post-activations for the current internal thought step. Crucially, a history of these post-activations, as seen in 5, is then used to calculate neural synchronization at 6. This synchronization, which measures how similarly neurons activate together over time, forms the core latent representation. From this synchronization matrix, specific pairs are selected, as indicated by 7, to create the actual latent representation 8 that the continuous thought machine uses to produce outputs and guide its attention mechanism 9, which then feeds back into the synapse model 10, completing the loop. It's a really dynamic process. Alright, so after seeing the overall architecture, listing 1 here shows us a simplified version of the continuous thought machine's code logic. It outlines the sequence, starting with processing input using a feature encoder, like a ResNet for images, for example. The core of it is a loop that runs for a number of thought steps. Inside this loop, attention is updated, pre-activations are computed by the synapse model, and then each neuron's private neuron-level model uses a history of these pre-activations to determine its new state, or post-activation. Finally, neural synchronization is calculated from these evolving post-activations to generate an output for each thought step. Okay, moving on from the high-level logic, listing 2 gives us a closer look at the code for the neuron-level models. Remember, each neuron has its own private model to process its history. This snippet shows how these neuron-level models are implemented. What's really neat here is the use of !einsum . Now, !einsum , short for Einstein summation convention, is a very powerful way to express complex operations on multi-dimensional arrays, or tensors, like matrix multiplications and sums, all in a single, compact line of code. It's particularly good for parallel computation. So in this code, after initializing some weights and biases, the forward pass takes the recent history of pre-activations for each neuron. The first !einsum operation then computes an intermediate representation for each neuron based on this history and its unique weights. Then, the second !einsum takes that intermediate result and computes the final single activation for that neuron. This efficient !einsum application allows all these individual neuron computations to happen in parallel, which is key for performance. Okay, so we've seen how individual neuron-level models process their history. Now, listing 3 details the computation of neural synchronization, which, as we discussed, forms that crucial latent representation for the continuous thought machine. This code snippet first shows an initialization step where pairs of neurons are chosen. Then, for each of these chosen pairs, learnable exponential decay scaling factors are defined. These factors, initially set to cause no decay, allow the model to learn how much to weigh recent versus older coactivity for each specific pair. During the forward pass, the code takes the history of post-activations. It then computes an exponential decay that's applied back in time, weighted by these learned scaling factors for each neuron pair. Finally, it calculates a weighted inner product of these decayed activation histories for the selected neuron pairs. This resulting "sync_representation" is what the continuous thought machine uses for outputs and to guide its attention. The authors note they actually use a more efficient recursive method for this in practice. Alright, so now that we understand how the continuous thought machine generates its internal representations and outputs through neural synchronization, let's look at how it actually learns. Listing 4 shows us the custom loss function. A key part here is how it calculates certainties for each thought step. This is done using entropy, which is a measure of how unsure the model is. So high certainty means low entropy, meaning the model is pretty confident in its prediction at that particular thought step. Then, instead of just taking the loss from the final thought step, or averaging across all of them, this loss function is quite clever. For each data point, it identifies two specific thought steps, the one where the loss was lowest, and the one where the model was most certain. The final training loss is then the average of the losses from these two particular steps. This approach encourages meaningful representations across different points in the model's internal thought process. Okay, building on that idea of using certainty and specific internal thought steps for the loss, Figure 3 now gives us a visual exploration of the continuous thought machine's performance and how this certainty behaves. So panel A here shows TOP5 accuracy on the ImageNet-1K dataset plotted against the number of internal ticks. We can see different lines for how the prediction is made, like taking the prediction from the instant tick, or the one where the model was most certain, or by averaging. Generally, accuracy climbs pretty quickly in the first 10 to 15 ticks, and then plateaus. Then panel B is a histogram showing how many data points achieve a certainty of at least 0.8 at each internal tick. This really illustrates that adaptive compute capability we talked about. Some instances get high certainty quickly, while others take more thought steps. And finally, panel C presents calibration plots. Model calibration. Well, it's a measure of how trustworthy a model's confidence scores are. So if a model says it's 80% sure, a well-calibrated model would be correct about 80% of the time for those predictions. These plots show that averaging the predicted probabilities up to a given internal tick results in good model calibration, meaning its confidence aligns well with its actual correctness. Alright, so figure 2 here gives us another angle on this adaptive compute idea, specifically looking at prediction rates versus internal ticks for different certainty thresholds. Panel A sets a certainty threshold of 0.5. We can see that the model makes a prediction for pretty much 100% of the data from around 4 internal ticks onwards. This means most examples reach this modest level of certainty quite quickly. However, panel B shows what happens with a higher certainty threshold of 0.8. Here, even after many internal ticks, the continuous thought machine only makes a prediction for about 80% of the data. This illustrates how you could tune this certainty threshold to decide when to stop the thought process, effectively trading off computation for confidence. It's clear that this continuous thought machine offers a really interesting way to manage computational resources, letting the model think more or less depending on the problem's difficulty. This ability to adaptively allocate effort is a significant step towards more efficient, and perhaps even more human-like AI. Well, that's all the time we have for today's AI Research Roundup. Thanks for tuning in, and I'm your host, Alex.